Hello.
Hello, hello. How y'all doing?
Guy who spent like half an hour locked out of his office because the door jammed.
The what now? The door jammed? What was that?
The lock of the office doors. Apparently, if you close them too hard, you
Mm,
have a hard time opening them.
you closed them too hard. So the moral of the story is don't slam your
Too
office door.
hard. I think I was rushing to the bathroom or something.
That's funny.
I didn't close it that hard, but if you close it not softly, it'll jam. You
Dang.
have a hard time opening it.
Totally noted.
How's everyone?
Yeah. There's an exam in pre-calculus next Monday, and yeah, so I'm kind of worried about that exam, and I'm worried about the students. They're struggling with logs. I'll say that much. Yeah.
Oh.
Yeah. Paco, are you in the Zoom seminar?
Yeah. Why? I mean, I get the emails, but I haven't attended this semester. So
That's fair. That's fair. What about you, Paco?
I'm okay, just got back in. I mean, yeah.
Yeah, I think I saw. Yeah, because I was gonna ask because I think I seen your name there sometimes. If I'm not mistaken, but I just don't know how much you're following it. I don't know how much AG you know. um,
Not a lot, but I'm catching up.
okay, cool. Yeah, nice.
I don't know, learning anything interesting.
Yeah, we're making some progress. Talking about Torai. I gotta keep up with that myself. I haven't been doing too much work towards it, but I think Freddie's giving a talk this Friday on some stuff, so that should be good.
During spring break?
Yeah.
All right, well, I guess you can do whatever you want on spring break. It's the nature of it.
Mm.
All right. Okay, well, yeah, so this is the last, so we will not be meeting on Friday for the same reason. Any questions? So if not, so today, what am I, I'm covering, I think it's chapter 8 of Ferrari's book today. So last time, yeah, some of these chapters are just going down in one lecture. So the last time we did chapter 7, basic facts about local fields. So today we're going to do chapter 8, the Brauer group of the local field. It has a little bit more than just that, but that's the main goal. And of course, we've already proven a result about the Brauer group of any complete discretely valued field with perfect residue field, of which a local field is a complete discretely valued field with finite residue field. But so there's a couple of other results we want to have anyway. Yeah, I guess the gist of it is that a lot of what we did will still apply, but the case where the residue field is finite, you can certainly say more. And then in particular, yeah, so maybe I'll flip back and find it. So what did we, sort of our main result about, yeah, hold on. Screen. Right. So this was from 2 lectures ago. Yeah, so we proved this, that if you have a complete discretely valued field, with perfect residue field K, then the Bauer group of the field is isomorphic as a commutative group to the direct sum of the Bauer group of the residue field and the character group of the residue field, the character group being continuous homomorph, being the Pontryagin dual of the Galois group, of the abelian Galois group of the residue field, or otherwise put, just continuous homomorphisms from the absolute Galois group. That should be a little k. Into Q mod Z. Okay. But I said isomorphic, and in fact, in this level of generality, so there was some short exact sequence that was split, and we chose a splitting, but it wasn't canonically split. So yeah, so in this level of generality, there's not necessarily a canonical isomorphism, but there most certainly is when the residue field is finite. So it's not that hard to see. In fact, it's really just a matter of touching up what we already did. Okay, so I know we want to prove some related things. In particular, we want to understand the Tate H0 of the multiplicative group in a finite extension of local fields. But let me say that better. We want to understand the co-kernel of the norm map in a finite extension of local fields. So that's really important. Yeah, which is very closely related to the Bauer group, by the way. I guess I didn't. I might come back and say it. I managed not to say this. It's true, by the way, that the Bauer group of a field is 0 if and only if the norm map on every finite extension of the field is surjective. Okay, and so then by hand we prove that the norm map of any finite extension of finite fields was surjective. So the one direction was basically what we did, but the other direction is also true. So because the multiplicative group of our local field is our target group for class field theory, we certainly do want to understand open subgroups of that group, and the norm map is coming into just the Galois homological business. What was I going to say? Anyway, so it turns out that a big piece of class field theory is understanding that the norm map is not surjective on a finite degree extension of local fields. The co-kernel is finite, and it has a lot to do with the extension itself. Okay, so we're getting towards that. So right, so until further notice, let capital K just be a local field, so a complete discrete evaluation field with finite residue field, which is excuse me, either canonically a finite degree extension of QP if it's characteristic 0, or non-canonically isomorphic to the Laurent series field over its residue field if it has positive characteristics. Okay, here's the first lemma. If you have a finite Galois extension of your local field where the Galois group is G, so any Galois extension, some of these results, the extension has to be cyclic or unramified, not this one. So then there exists a submodule of the unit group, in fact, of the first unit group, the units that are congruent to 1 modulo the maximal ideal, the ones that reduce to 1. So there's a G submodule that has finite index in the unit group that is cohomologically trivial. So remember, that means that for all the subgroups of G, the higher for all subgroups H of G, the higher H cohomology groups vanish, and then we showed that's equivalent to the same thing with the vanishing of all of the Tate cohomology groups. Okay, so let's prove this. This is a kind of nice proof. Sort of some nice local field stuff going into this. So first of all, let's just take an easy case of our number theory 1 square, right? So R is the valuation ring of K. L over K is a finite degree Galois extension. Everything is complete though, so the integral closure of the valuation ring downstairs is the valuation ring upstairs. That's very nice. So by V sub K, I'll mean the downstairs valuation, and by V sub L, I'll mean the upstairs valuation. Okay, so like any finite degree Galois extension, it has a normal basis. What does that mean? It means that there's an element of the larger field non-zero so that the orbit of that element under the Galois group gives you a K basis for the extension. Okay, as we saw and used, this is equivalent to saying that the additive group of L is induced as a module. No, it's equivalent to saying that it's isomorphic to Kg as a Kg module, and which implies that it's induced. Okay, so right. Okay, so this normal basis doesn't necessarily have any integrality properties. So the first thing I'm going to do is I'll just scale it so that it does. So if I choose any element of the downstairs field, certainly scaling things by a scalar, an element of the downstairs field, does not change the fact that it's a normal basis. And if I just choose the valuation to be large enough, then of course, well, then again, the upstairs valuation and the downstairs valuation only differ by a constant multiple at most. So that's fine. So if you scale things by a sufficiently integral element, you can make all the elements integral. Okay, and so now I'm going to define M to be the R submodule generated by this integral normal basis. Okay, so this is a very nice R submodule. This is in fact, okay, first of all, even integrally, this, so yeah, it literally is an integral normal basis. What does that mean? It means as a G module, it's isomorphic to the group ring RG. Okay, moreover, it's an R lattice in L. What does that mean? Well, again, if you have a Dedekind domain and then you have a finite degree, if you have finite dimensional vector spaces over the fraction field of your Dedekind domain, you can talk about R lattices, which are, what is an R lattice? An R lattice is an R submodule of a finite dimensional K vector space, which is finitely generated. And I guess projective should be automatic here, but if not, I'll say it, and spans the vector space over K. Okay, so it's just that's what an R lattice is. For instance, the ring, any order in a number field is a Z lattice in the number field, so it's that kind of thing. Okay, so M is an R lattice, and then any R lattice over a DV, any two R lattices are kind of commensurable with each other. You can make one be contained inside the other just by scaling by a power of the uniformizer. Okay, so that's not hard to check. So if I take any downstairs uniformizer, this is what I just said. So what am I just have an R lattice M. What's my other R lattice? Well, S itself is an R lattice. Okay. And so I don't know which one is, in fact, I know that M is contained in S, and I kind of want it the other way around, but no problem. Easy to show that if I scale S by a large enough power of the uniformizer, like any R lattice, it will be contained in any other R lattice. Okay, so what? So where are the groups? The groups are going to be, it's kind of like it's like an analog of the higher unit groups, only you do it with respect to this lattice M rather than with respect to the entire ring of integers S. That's basically what's going on here. Okay. So Vn is going to be, for slightly technical reasons, which this n is again defined this way. And so Vn are, well, it's exactly what it looks like. They're elements that if you subtract one, then they're of the form some element of this lattice times a pretty big power of pi. Okay. And so, yeah, so here there's like a two-line calculation that I did, and then I omitted it. But you can, the one thing here that's kind of not completely obvious is that Vn is actually closed under multiplication. It's certainly clear that every element of Vn, well, every element of Vn is congruent to 1 modulo pi. So Vn is certainly contained, yeah, maybe I should say it now. So certainly Vn is contained inside this first unit group. How do I know it's a multiplicative subgroup? Well, you have to write it out, and you'll find it's no problem to write it out, but you are using the fact that M contains pi to the n times S. Okay, so you check that Vn is a multiplicative subgroup, and yeah, so the V that I want here that's going to be cohomologically trivial, I believe, is actually just going to, I mean, they'll all be cohomologically trivial, but I'm going to take I'm going to take v sub 1. Okay. So how are we doing this? Pretty easily, actually. So again, this is also a generalization of a very familiar fact, a fact that I've used at least once or twice in the last week. So you know that un modulo un plus 1 is canonically isomorphic to the residue field. And so this is a very mild generalization of that. What is the map here from Vn mod Vn plus 1? It's really kind of amusingly simple-minded. What do I know about Vn? Well, if I subtract 1 and divide by pi to the n plus n, I'll get an element of m. That's my map. I'm going to subtract 1 and multiply by pi to the minus n. So that certainly takes me an n. The thing that's not completely obvious here, again, that you're checking is that this is a group homomorphism where you put the multiplicative structure on Vn and the additive structure on M. So there's somehow there's something logarithmic happening here, or multiplicative to additive happening here. And most of the time you can't just take a multiplicative group, subtract 1, and get a homomorphism to an additive group, but you can here, and I hope you've seen it for for the study of local fields. Okay. It's because of this, the way that it's defined. Okay, so it's clear that this is defined. It's clear that it's surjective because, again, that's kind of what Vn is. You'll get all of m by subtracting 1 and dividing by pi to the n plus m. And well, when is it divisible by 1 more power of pi? Well, if and only if you are in Vn plus 1. Okay, so except for the fact that this is a homomorphism, it's completely immediate. Okay, so it really is obvious that this is a bijection. So you check that it's a group homomorphism. Easy also to check that this is a Galois equivariant map. Okay, why is that helpful? Well, just like in the usual case, this was the residue field. This is going to be a similar version of this would have been, in fact, this would have been the residue field, little l of capital L. If you think about this, really what I'm doing is there's various ways of saying this. I'm taking something which is isomorphic to the group ring Rg, and I'm tensoring it from R to R mod pi. You can think of it that way if you like. And so therefore it's isomorphic to the group ring R mod pi of G, which is little kg. I guess that's, there we go. Okay, so that's nice. And so therefore, well, a G module which is isomorphic to anything bracket G, those are precisely the induced modules, and so therefore this guy is induced. So therefore, is its isomorphic module Vn modulo Vn plus 1. Also clearly, so this is a group ring where the ring is finite. It's the finite residue field little k of capital K. The group is finite, so a group ring is finite if and only if both the group and the ring are finite. And so at the same time, we've shown that Vn mod Vn plus 1 is finite, and also that it's induced, therefore it's weakly projective equals weakly injective, therefore it's called logically trivial. Okay. Now here's an argument. It's kind of funny to me because like this is translated from French to the extent it's not like perfectly translated, but it's translated well. So in Serre's local fields in Galois cohomology, he used this word that I learned as a graduate student reading it, dévissage. What is this? This the actual literal translation. Does anyone know what dévissage means? It means like unscrew it. Okay, and so so what does he mean? He means that like you have something where you have your object and you have some finite filtration, and you make an argument on each successive quotient of the finite filtration, and then you deduce something for the entire thing. So you basically prove something by breaking it up into finitely many pieces and looking at each piece, right? And so in other words, what do I have here? So I have like my V1 inside V2, very no big deal, just a finite filtration. And so obvious, of course, if the successive quotients are finite, then the first one modulo the last one is finite. And then if you just think about a bunch of, if you think about all of your short exact sequences, you are going to get from this that that V1 modulo Vn is also cohomologically trivial. Okay. Yeah. Okay. So sure. Okay. All right. So therefore, V1 mod Vn is cohomologically trivial, and now we're basically done. Although the last step is not going to be, it's going to be a little unsatisfactory, as you'll see. So again, also we're in a situation where all the groups in sight are profinite groups here. They really, I mean, in particular, they're open subgroups of the unit group, which is a profinite group, and so they're profinite. And again, the profinite topology is being defined by this family of subgroups. Okay, so again, you know, as long as you, what am I trying to say? Well, whatever, maybe I won't say it in words, but it's quite, if you just think about it for a little while, it's clear that the Vn are cofinal in the family of all open subgroups of the unit group of the field, in the sense that every open subgroup contains one of these Vn's, and so that's what you need in order to be isomorphic to the completion. And so yeah, so as like we've seen stuff like this several times before recently. So V1 is not, first of all, V1 is complete, right? It's profinite, but it's complete, you know, by passing. We don't need to pass through all of the open subgroups. We just need to pass through a cofinal system of them, and Vn, I claim, is a cofinal system, and so therefore V1 is isomorphic to this inverse limit. Okay, what's the point? The point is that I have my V1 as a inverse limit of finite modules, and my modules are over a finite group. And if you think about it for a second, this is the type of passage to the limit that we haven't used yet. Before, we were passing to inverse limits on the group side and or direct limits on the module side. And we said that works great. Either way, they come out as direct limits in terms of the Galois cohomology. Here, I'm trying to pass to the inverse limit on the module side, so I haven't done that before. If you think about it for a little while, if you, you know, the Galois cohomology is contravariant in the group and covariant in the module. So if anything would be true, then the inverse limit should pull out as, again, an inverse limit and not a direct limit anymore because it's covariant. Okay, but it's not, it's, you know, no one said, you know, that you could do this. Well, actually, Harari did say that you could do this. I just haven't mentioned it up until now. So this is indeed a result, not a tough result from chapter 1, which I think I just skipped because I wasn't going to need it for a long time, but now I need it. If you have a finite group and you have an inverse system of finite G modules, not a totally abstract inverse system, an inverse system parameterized by the positive integers, you know, so maps from AN down to AN minus 1, etc. Then you can do what you want. Then passing to the inverse limit commutes with the group cohomology. Okay, again, you know, good thing we have a textbook. We don't have to prove every old thing that we don't want to. Okay, and then you apply the result, and you get okay. If you therefore you find that in particular, as a, you know, just by staring at this result of Harari, you see that if you take an inverse limit of a sequence of modules for a finite group, if each module in the sequence is cohomologically trivial, then the inverse limit is cohomologically trivial, and that's just exactly what we wanted because we have V1 as an inverse limit of V1 might be. Okay, so it's a nice technique. All right, so now, yeah, so here's a very important result. Again, we're sort of working our way towards these things. I really want to know what the co-kernel of the norm map is, let's say for any finite Galois extension of a local field, okay? And now I'm doing it for a finite cyclic extension, okay? I guess I especially want to know it for any finite abelian extension, but this is, okay. So here's the result. The result is that indeed, the norm map is not surjective, except of course if the extension is trivial, in which case it certainly is. Okay, so the index of the image of the norm map is precisely equal to the degree of the extension. Okay, so this is a very, very important result. Again, this is really foundational towards towards a lot of the classical theoretic results. Okay. Yeah, you may want to begin to wonder, what does, what do finite abelian extensions of K have to do with open subgroups of K star, and what does the norm map have to do with it? So I'll leave it as a question, and this is like a piece of evidence for that. Okay. I mean, I'm only telling you what the index is. I'm not telling you, like you could also ask like which subgroup of K star are you getting as the image of the norm map here? Okay. Sorry, yeah, I have some exploding pen on there. You probably can't. Yeah, you can see it. All right. Anyway, right. So let's look at the proof. Yes, this is a satisfying proof in terms of what we've done already. So I'm interested in the co-kernel of the norm map. I'm going to be a little fancy about it. That's the Tate H0, as we know. But we also know that the Tate H1, otherwise known as the ordinary H1, is 0. That's just Hilbert 90. Okay, why is that helpful? Well, if you remember, things are really much better for finite cyclic groups. All the odd numbered Tate cohomologies are the same. All the even numbered Tate cohomologies are the same. And then more than that, there's a kind of there's sort of functorial, there are relationships between the odd Tate cohomology and the even Tate cohomology, which was formalized in this very pleasant, easy theory of the Herbrand quotient, which we spent, I don't know, 25 minutes one day talking about. It was really no big deal. And now we're in a position to use the Herbrand quotient. So we know what the order of the H1 is. It's a trivial group, so it has order 1. So if we're trying to show that the Tate H0 has a certain order, then we should be trying to show that the Herbrand quotient has that order. Okay, so that's a good idea. All right, and so now we can use, we have all these results. The Herbrand quotient of a finite module is 0, 1, always 1. The Herbrand quotient is a positive rational number. In a short exact sequence, the Herbrand quotient of the thing in the middle is the product of the two things at the ends, etc. Okay, so let's let V1 be as in the lemma that I just proved. So a particular subgroup of the unit group that has finite index and is cohomologically trivial. Okay, so it has finite index, so therefore it's finite. Okay, that's one of our properties of the Herbrand quotient. The Herbrand quotient of any finite module is 1. And we have this short exact sequence. That's another property of our Herbrand quotient. Okay, so the Herbrand quotient, well, V1 is cohomologically trivial, so the ratio of the two things is definitely 1 because the numerator and denominator are both 1. And then again, the Herbrand quotient of U would be the Herbrand quotient of the first guy times the Herbrand quotient of the last guy, but the first one is 0, and the last one is 0, and so therefore the Herbrand quotient of U is equal to 1. Okay, well, we didn't want U, we wanted L star, but there's a short exact sequence relating U to L star, right? Namely, the valuation is a homomorphism, surjective homomorphism from L star onto Z with kernel U. So we have that short exact sequence, U goes to L star goes to Z is the short exact sequence. And so again, the Herbrand quotient of L star is equal to the Herbrand quotient of Z times the Herbrand quotient of U. But I just said that the Herbrand quotient of U was 1, so really it is the Herbrand quotient of Z. Well, that sounds easy. Well, Z is a trivial module, so how does the H0 act? So it's the invariants are itself, and then the norm map on a trivial module is just multiplication by the order of the group, because the norm element acts as, every group element acts as 1, so the norm element acts as the order of the group. And so, okay, therefore the Tate H0 of Z for any finite group is Z modulo the order of that group, okay, which is L over K. That was the H0. What was the H1? Well, again, it's H1, but it's trivial action, so that's just a Hom. So I have a Hom from a finite group into a torsion-free group. No, I don't. These homomorphisms all have to be trivial. So great. The top guy has size L over K. The bottom guy has size 1. Therefore, the Herbrand quotient has size L over K. Again, the denominator I know is equal to 1, so therefore the numerator really must have size L over K. Okay, so can't argue with that. All right, so the next result is really just touching up a result that I did 2 lectures ago, okay, kind of in more generality. Well, okay, kind of, we'll see. So now suppose I am assuming something very strong. I have a finite Galois unramified extension. So these, of course, bijectively correspond to extensions of the finite residue field, right? We have one of them of every degree. Okay, so let's let G be the automorphism group. Okay, that's going to be cyclic group of order equal to the degree of L over K. And my claim is that the unit group and the first principal unit group U1, again, the ones that are 1 modulo the maximum ideal, are cohomologically trivial. Okay, so yeah, so I'm being very systematic about this. On page 7 of lecture 14, we saw, even in more generality, whenever we had a complete discrete valuation field with perfect residue field, the quotient UN by UN plus 1 was an induced G module, hence cohomologically trivial. Okay, let's flip back. I don't believe it. Did we actually prove that? Yes. So we proved that UN modulo UN plus 1 was isomorphic to the additive group of the residue field, which is indeed an induced, again, the Galois group is canonically isomorphic to the Galois group of the residue field. So this is indeed induced. And then you see that I just didn't say it was induced last time. I just applied the fact that it was acyclic for Galois cohomology. Okay. By Serre's lemma, what was that? That was this other thing about inverse limits that came up in that lecture. Some version of it gets done in this chapter of Harari. I think he does the special case of it he needs, and then he has an exercise where he develops full result. Yeah, here's Serre's lemma. You have a finite group, you have a decreasing filtration of G modules such that the first one is complete and separated for the induced topology. In other words, that means that M1 is isomorphic to the inverse limit of M1 mod Mn. And then if the cohomology, this is also a Desvisage type argument, kind of an infinite Desvisage type argument, so you use the completeness. If the successive quotients have Qth cohomology 0, then the whole thing has Qth cohomology 0. Okay, so we're still in a situation where that applies, right? And so what did we show last time? We showed that, so again, we get that HQ of G U1 is equal to 0 for all Q greater than or equal to 1 because I passed to the limit off of some induced modules. Okay. Right, but now the only thing is I want to show that the thing is cohomologically trivial. So what does that mean? That means that it's acyclic for H cohomology for all subgroups H of G. And you ask yourself, gosh, is that going to be any more trouble than what we just showed? And the answer is no, it's no more trouble at all than what we just showed. So if I started with a finite unramified Galois extension whose Galois group was G. And so just by the magic of Galois theory, if I take any subgroup H, well, H is the Galois group of L over LH. If this guy is unramified Galois, then, I mean, in general, the top one is always Galois. In this case, the top one is always Galois. and the tower is unramified if and only if both of them are unramified. So all we have to do is run the exact same argument through with K replaced by LH, okay, and the exact same thing works. And so then we get that the H cohomology of U1 is also trivial for all Q greater than or equal to 1. And so by definition, that is exactly to say that U1 is cohomologically trivial. Okay, but now I just want the same thing for U. Okay, so again, we also showed in that lecture that this is not very surprising. How in the world could we have showed this? We must have used this short exact sequence, right? So again, the entire unit group modulo the first higher unit group is naturally this literally is like the definition of U1, right? So this is the reduction map. You know, U is what am I called, like S, I guess, probably, since it's upstairs. So this map is literally the map on units induced by the reduction modulo of the maximal ideal, and U1 is the kernel of this map by definition. Okay, so we have that kind of short exact sequence, right? And we know that U1 is cohomologically trivial, right? And so therefore, for if we for all the Tate cohomology groups, even that should just literally give us an isomorphism between the Qth Tate cohomology of U and the Qth Tate cohomology of the residue field here. Right, everything is in the right place. No boundary maps or anything like that. So that's what we got, right? And we stopped here in general because in general, okay, I guess I guess maybe. In general, I know that when Q equals 1, this is 0 by Hilbert 90. I don't know that in general for higher Q. In fact, when Q equals 2, this is the Brouwer group of some finite degree extension of my residue field L over K. I'm like, what? No, the Brouwer group doesn't have to be 0, in general. But that's the point. The point is that for us, now all of our residue fields are finite. And so we know that not using any new ideas, just using the fact that we're imposing stronger hypotheses, now we know that the H2s are 0 as well. Okay, that's what I'm saying here. So again, in full generality, we would have had that the H1 for any subgroup was 0. That's Hilbert 90. But now, in general, the H2, again, is this relative Brouwer group, but where K prime is whatever the residue field of LH is. It's somewhere between K and L, so it's finite. Okay, but again, we know that the Brouwer group of a finite field, or a relative extension of finite fields, is finite. So what? So now all I know is that the H1 and the H2 are equal to 0 for all the subgroups. Cohomologically trivial means I'm supposed to prove the vanishing of all the H's for all of the subgroups. Well, if you don't remember this one result, that sounds like it should be a lot harder, but apparently we can flip back to page 2. Whoa, that worked out nicely. Of lecture 9. There it is. And we had, this was really one of our best results in the kind of pure cohomology theory of finite groups. What it says is that no. If you have a module that is, if two consecutive Tate cohomology groups are vanishing, wow, that's okay, never mind. It doesn't look as gross in real life as it does on the camera, I'm sorry. Okay, so if you have two consecutive Tate cohomology groups that vanish, even just for all the CeLO P subgroups, so certainly still more if they vanish for all subgroups of G, then that's it. You're cohomologically trivial. You're even cohomologically trivial for all Tate cohomology. Okay, well, that's exactly the situation that we're in. We have two consecutive indices, namely 1 and 2, okay, where again, it vanishes for all subgroups of G, so in particular for the CeLO P subgroups of G. And so by some of this theory that we've worked on, we're getting that U is cohomologically trivial. Okay, so that was nice. Well, what did we just prove? Yes, we just proved that for a finite Galois unramified extension, the unit group and oops, I mean, by the way, like, there's no reason to stop at U1. I'm quite sure that the same argument is going to prove that all the higher unit groups are homologically trivial. Okay. Right, and so yeah, so here, just a reminder that the reason that we couldn't do it last time is only because it isn't true in the previous level of generality. For a perfect residue field, what if the complete discrete valuation field was like, I don't know, like QP Laurent series field over that? Well, then the Bauer group might not have been 0. And then again, the argument still correctly would show that the principal unit group U1 is homologically trivial, but really the entire unit group, because it is a Bauer group that just doesn't have to be 0 in that level of generality, then therefore the entire unit group might not be homologically trivial. So we're actually starting to use in some sense, I mean, if I'm going to make a big deal over nothing, in some sense, we're turning the corner here from a general study of Galois cohomology to a study of local fields, because this is just, there's no like work hard or prove a generalization. This is just a special thing, which is true when the residue field is finite. Okay, let's see. So if we can pass to the limit, and so let's have G be the Galois group of the maximal unramified extension, which is an infinite degree algebraic extension of K, which again, as we said last time, upon reduction modulo the maximal ideal, is canonically isomorphic to the Galois group of the residue field, which is also isomorphic. We'll make this isomorphism canonical in a second with Z hat. Okay, and so we pass to just passing to the limit, we get that the unit group of K on RAM is again cohomologically trivial. All right, so now I want to just trace over the computation of the Bauer group. So again, previously we saw that in any complete discrete valuation ring with perfect residue field, the Bauer group of the upstairs field is isomorphic to the Bauer group of the residue field, direct sum the character group of the residue field. And again, if we apply that to our local field K, for which the Bauer group of the residue field is 0, I get that the Bauer group is isomorphic to the character group of the residue field, which is Q mod Z. But I don't just want it to be isomorphic to Q mod Z. I want a specific isomorphism, and then I'm going to explore how this isomorphism works with respect to restriction and co-restriction. I'm very serious about this isomorphism. I'm going to build local class field theory around this isomorphism. So I don't just want to say, hey, it's isomorphic. I want to tell you a map. Okay. So no problem. I mean, we kind of did it before. So I'm literally just going back and being more careful. There's nothing else actually happening here. So one thing that we proved, this was kind of, I took the easy way out. I told you the theorem of Lang that the maximal unramified extension of any complete discrete valuation field with perfect residue field was C1 and therefore had vanishing Bauer group. It's a lot easier to prove that the Bauer group is vanishing than to prove that the field is C1, but what I said was short. Okay, and so therefore by definition, the Bauer group is Galois cohomology of the maximal unramified extension. This is again relative Galois cohomology, Galois group of K on RAM over K. So now I just claim, so I have these guys. And so now I just claim that actually I have 3 canonical isomorphisms that will take me from this relative Bauer group to Q mod Z. Okay, so I know something called beta, which I'll tell you what it is in a second, to H2G with coefficients in Z. Then I'm taking the inverse of some other isomorphism called delta to go from H1 from G to Q mod Z. And then I'm taking some other isomorphism gamma that is taking me to Q mod Z. What are these 3 maps? No, I mean, they're not hard and we've seen them all before. I'm just being careful. So again, we have this unit group sequence. This is literally just the evaluation. The field is not complete anymore, by the way, because I took an infinite degree extension, but that's okay. Okay, and so I just took the trouble of telling you that this guy was cohomologically trivial, and so therefore that is going to induce an isomorphism between the G cohomology these guys and these guys. But whereas before, like one of the ones on the ends was cohomologically trivial, and that just gave us an isomorphism on the corresponding cohomology groups with the same index. This time it's the one in the middle, which is cohomologically trivial. So if you do the long exact sequence, there's a connecting homomorphism. Wait, I think I confused myself. Let me think for a second. Yes, I did confuse myself. In fact, I said something wrong. It's you, which is cohomologically trivial. It's you, you're cohomologically trivial. Okay, so that's what I just proved. And so therefore, all that nonsense I was just chattering was wrong. So that one's cohomologically trivial. So sure, we get an isomorph just taking the exact sequence of cohomology. Every third one is equal to 0, and this just gives us an isomorphism from H2, this guy, into H2 of that guy. So that's beta, no problem. Just the, I mean, this is literally the, so this is the induced map on H2 from the valuation map. That's all it is, okay? What about delta? Well, we saw that one before. That comes from this short exact sequence. And Q is always acyclic for Galois cohomology, as we discussed before, because if you take cochains and coboundaries, you're still going to get a, they're all going to have a structure of a Q module. And then if you do it for any finite group, you're gonna find that the cohomology groups have the structure of torsion vector spaces over Q, but there are no torsion vector spaces over Q. So Q is totally acyclic for Galois or profinite cohomology. Take your pick. Okay. And so what does that do? Here there's this time there's a connecting homomorphism. The one in the middle is cohomologically trivial, so that gives us an isomorphism from H1 of Q mod Z into H2 of Z, and apparently I want to go the other direction. So I take the inverse, but it's very explicit. You know, that's the point. They're all very explicit. What's this last one? Well, this is just some kind of Pontryagin duality. So for the gamma, G is the, I think I sort of changed my mind here. That's not what it is. It's isomorphic to it, but it's literally equal to that. And so, yeah, I forgot. I think I wrote that and then I decided to be more careful. So very, very carefully, because the automorphism group of K on RAM over K is isomorphic under reduction modulo the maximal ideal to the automorphism group of FQ bar over FQ. Not only is the absolute Galois group of FQ isomorphic to Z hat, it has a canonical topological generator, namely the Q power Frobenius map. And so therefore I want capital F to be the thing that maps that under this isomorphism maps to the Frobenius map. So for whatever reason, I decided to be very explicit about it. So therefore, there must be a unique automorphism of K on RAM over K, which under reduction modulo the maximal ideal maps to the Q power Frobenius map. What does that mean? It means F is the unique automorphism, so that for all X and K on RAM, if I compare F of X to X to the Q, yeah, there's no way that X to the Q is an automorphism in characteristic 0, but at least once I push it down to the its image in the residue field should be equal, and therefore the valuation of the difference should be positive. Okay, so I mean, whatever. I'm just writing out. I got excited about being careful, so I just wrote this out very, very explicitly and very carefully. And so, okay, and so now I have a group. Not only is my group G topologically cyclic, isomorphic to Z hat, but I have a canonical topological generator. So now if I have a continuous homomorphism from that group to Q mod Z, that's what I have, because of course this is trivial. So the H1 is a hom. In profinite cohomology, all the cochains are always continuous. So these are the continuous homomorphisms from my topologically cyclic group with a canonical generator into Q mod Z. How do I get an element of Q mod Z from such a homomorphism? I know I will evaluate it on my canonical generator. Okay, so we're just, again, we could have said all this before. We're just being explicit, but so we have, you know, at least, in principle, we really could track this map through. Okay. And so having been so careful with the definition, I'm now going to bail out on the proofs of the functoriality properties. They're pretty straightforward. Bye. Okay. So yeah, so by the way, this canonical isomorphism gets a name. It's called the invariant map. Okay, so this, you heard it here first. This is the invariant map is this particular isomorphism from the Brouwer group of a local field to Q mod Z. And now I want the functoriality properties of the invariant map under restriction and co-restriction. And again, it's not the hardest thing in the world, but I'd like to, if I skip this, maybe I could talk about like Lubin Tate modules or something. I need to be skipping something. So here's the result from 8.4 of Harari repeated in theorem 8. I guess the way that I'm stating this is literally the first part of theorem 8.9, but the proof of it is given in 8.4. And so, yeah, we always have restriction maps from any, if you have, as we said, if you have any extension of fields, actually, you have a restriction map in Galois homology. Okay. And so, yeah, so this guy is finite degree. I'm not assuming anything about it. It doesn't have to be Galois, doesn't even have to be separable, unless K is characteristic 0, in which case everything has to be separable. Then the restriction map, again, I just have an isomorphism. So what is the induced map on Q mod Z? Q mod Z is a pretty easy group, right? It's just a direct, I mean, this, like, you can think of this as the group of all roots of unity and the complex numbers. It's just a direct limit of Z mod NZ. So it should be a pretty easy map. And so what it is the map is multiplication by the degree. Okay, so this is the, if you just look carefully at what this map is, you can prove this, okay? What about the other way? This time I do have to assume that the extension is separable, okay? I have a co-restriction map in the other direction, and whereas restriction multiplies by the degree, co-restriction is the identity. I said I wasn't going to do it, but if you think about it for a second, I can deduce what co-restriction does from what restriction does, because I just, just pushing back and forth via these isomorphisms. And I certainly know that restriction followed by co-restriction is multiplication by L over K. So if I know that restriction is already giving me multiplication by L over K, and I just go back and forth via these isomorphisms, then that will tell me that co-restriction has to induce the identity. Okay, so now we understand, and let me just make a remark here. This is actually really cool because a lot of times in Galois homology, you don't just want to compute your Galois homology group over the field. Usually, whenever you have a Galois homology group over your field, it's equally interesting to understand. Again, you have a restriction map to every well, let's say every separable finite degree extension, and it's often very important to know the Galois homology over your field, to know the Galois homology of GL, where L is your algebraic extension field. But then you do have this restriction map, and it's often like very, very, very important to know what the restriction map on Galois homology is. Okay. And so here we're doing this for the Brouwer. And again, this definitely for the Brouwer group of any field, knowing what the Brouwer group of the field is as an abstract group is actually not that interesting. It's probably isomorphic to like a bunch of copies of Q mod Z or something, like or something, it's probably like a really big torsion group. So like maybe not that interesting as a group. I would love to know if I have the Brouwer group of a field and then I have an algebraic extension of my field, I would love to know what that restriction map is. That's much more important. And so here what we're saying is that the restriction map is very simple. The relative Brouwer group, namely, which we proved this, the relative Brouwer group are the ones that are killed by restriction to L, and the ones that are killed by restriction to L are precisely the ones that are L over K torsion. Okay, again, by res co-res, we would have known that if you're killed by restriction to L, then you're killed by restriction followed by co-restriction. What is what is killed can only, yeah, it's like, okay. If you're killed, you have to stay dead under the next homomorphism. And so in complete generality, for any finite degree extension of fields, the Brouwer group of L over K must be contained inside the L over K torsion subgroup of the Brouwer group of K. The fact that it's equal is a remarkably simple result. Okay, so this really is, this is computing the Brouwer group of a local field functorially, which is much more important. Already, by the way, I mean, I should say that if you're doing arithmetic geometry and you're studying rational points or lack thereof on varieties over a field, this is something I really like to do in the first half of my career. It was probably my favorite thing. Again, if you're looking at there's a certain you're looking at divisor classes, you're looking at period and index of these varieties, you're looking at degrees of rational zero cycles and rational points on your variety. There's a certain thing called the period index obstruction map, which takes values in the Brouwer group of the field. I may have mentioned this very quickly last spring. And so in my own work, I definitely find myself wanting to know what the Brouwer group, I have some Brouwer class which is not zero, and I want to know like what happens to that Brouwer class after I restrict to some finite extension. So what I'm saying is this type of very simple relationship on the Brouwer group is really helping you understand rational points on varieties over p-adic fields. Okay. All right. And so I think I'll just end by stating two theorems that I don't want to prove, which, well, I guess I couldn't prove them if I wanted to in the time allotted. So yeah, so here's one result, which is on the cohomological dimension of these local fields. The action comes in at the end at any prime different from the characteristic of the field. This is still a local field. Then the L cohomological dimension of the Galois group is equal to 2. For sort of silly reasons, if your field is characteristic P, I think I explained this last time or a couple times ago, if your field is characteristic P, the cohomological dimension at P has to be 0 or 1. So that's, if we're in the case of a Laurent series field, that's true here. And so the cohomological dimension at P would be equal to 1. Well, that's less than or equal to 2. So the cohomological dimension of the Galois group of any local field is going to be equal to 2. There's a couple of auxiliary results there, but maybe I won't get into them. But yeah, so the fact that the fact that local fields have cohomological dimension 2 is a basic result about the complexity of local fields. Okay. And then here's another result. Yeah, I was looking ahead a little bit. I'm realizing I'm just going to have to completely skip, I think, this chapter on Tate's duality theorem for finite modules over a local field, just because there's no way that I'll have time to get to global class field theory if I cover it, which is a shame because that's very useful. Tate has a duality theorem, a local duality theorem for abelian varieties over a local field. That's, both results are called Tate local duality. The abelian variety one is very useful to me, and the proof of Tate local duality for abelian varieties rests very strongly on Tate's local duality for finite G modules. Okay. Anyway, but we can prove this. If I have a p-adic field and I have a finite GK module, then all of the Galois cohomology groups are finite. Okay, this is not going to be true for global fields, okay, which would be easy to see that it's not true for global fields. So this is this is basically an expression of the fact that the profinite group of a p-adic field is small in the technical sense, that it has only finitely many quotients of any given size. Okay, unless there are any final questions, this is it for today, and then we have spring break on Friday, and then we come back and talk about more class field theory on Monday. All right, well, See ya.